My name is Brent Young. I'm president of AOSense. I really appreciate the opportunity here to describe what we're doing here at AOSense on quantum sensing. The quantum sensors have an exciting potential for enhancing capabilities in defense, national security, and commercial applications. Although AOSense has participated in projects addressing a broad range of these applications, our primary mission has been to transition quantum atomic sensors and advanced atomic clocks from physics laboratories to fielded systems that will improve navigation and timekeeping in GPS-denied environments. Atoms have the capability to ultimately support navigation with inaccuracies less than about 5 meters after 24-hour navigation time. This represents a 200-fold error reduction relative to the typical half nautical mile per hour navigation errors of conventional aircraft navigators today in the absence of GPS. The world's best atomic clocks, of course, have achieved much lower errors than we target here. However, those are laboratory clocks that are unsuitable for field applications. Our objective is to enable operation on moving platforms while maintaining performance exceeding that currently available with existing mobile atomic clocks. One of the appealing aspects of quantum atomic technologies is the broad range of modalities in which they can operate. For conventional sensors, high-performance gyroscopes and accelerometers employ very different technologies. However, the commonality of atomic devices has enabled AOSense's modest 30-person staff to contribute significantly to the broad range of quantum devices indicated here. A green check indicates AOSense's development of a laboratory prototype. We give ourselves a gold star whenever an independent external laboratory validates our sensors. When AOSense first started developing quantum atomic technologies in 2004, component technologies suitable for fielded systems in dynamic environments were severely lacking. Over the past 17 years, AOSense has developed a variety of enabling technologies, which we now sell commercially. So this next slide shows a variety of AOSense's photonic, electronic, and vacuum products that enable robust, low-swap quantum technologies. For example, our lasers and laser drive electronics provide high performance in low swap packaging. The unique feature of our optical isolators is that they provide much higher transmission at 780 nanometers and 850 nanometers than competing miniature isolators. We sell our high flex cold atom beam system to premier research groups around the world. They enable these groups to focus on physics research rather than engineering an atom source. Within the next few years, quantum atomic gyroscopes will revolutionize high accuracy GPS denied navigation. In 2021, just a couple months ago, DARPA approved for public release AOSense's 2009 gyroscope results from our precision inertial navigation systems effort. So those results are shown here. On a modest budget, the gyroscope achieved truly exceptional angle random walk and bias stability. Imagine that you take a circle and divide it into 360 degrees, then divide a degree segment into 1 million parts to get 1 microdegree angular subdivisions. You would need to wait 1 hour to observe a 1 microdegree drift of the pin's gyroscope. This graph compares the performance that quantum atomic gyroscopes in general, that's what this bubble is right here, can achieve relative to a variety of other conventional technologies, which have benefited from over $1 billion funding over about 50 years. So it's really rapid progress we're seeing here. Subsequent, and the red line here indicates the bias and stability of the AOSense gyro. Subsequent AOSense research has focused on reducing swap and enabling robust operation under high dynamics. The next step is combining multiple quantum atomic inertial sensors into an atomic IMU, or inertial measurement unit. Many consider quantum atomic inertial sensors to be relatively immature technologies that are years away from practical applications. However, AOSense first completed and shipped a portable single-axis quantum atomic gravimeter over a decade ago. Although this low-budget portable system traded off performance relative to previous larger systems, the strength of the atomic reference is evident in the observation shown in the plot on the right of the lunar solar variations due to the relative motion of the sun, earth, and moon. After demonstrating portable sensors, our next step was to initiate the development of mobile sensors, which can actually operate while on a moving platform. An AOSense IRAD project developed the quantum atomic gravimeter on the lower left, which can function in any orientation. A van transported this sensor starting in the AOSense loading dock, heading up to Skyline Boulevard to the west, returning to AOSense, continuing to Mount Hamilton to the east, and then returning to AOSense loading dock. The gravity measurements, which we collected in a stop and go mode, exhibited good retrace for measurements of local gravity at various altitudes. Further development should support mobile gravity data collection. Finally, we are excited about the prospects of quantum atomic absolute gravimeters for geophysical exploration and national security applications. This table compares the target performance for AOSense absolute gravimeter under development with the performance of competing technologies. The boxes below highlight the significant volume reduction that we anticipate. We would encourage you to contact us with any questions you have about either our R&D services or products. Thanks for your attention.
You actually, so this is a real working unit that you put in a van.
Yep.
And you drove it around and you made measurements and you measured the difference in milligauss on repeated runs of driving it around to show that it works.
Yeah, that's right. So in the plot you see is kind of a time sequence on the horizontal axis. It indicates the run number of different measurements we make. And then the vertical axis indicates the gravity measurement, where it's relative to the measured value in the AOSense laboratory. And the US NGA had made a measurement of what the gravity was in the AOSense laboratory. And so we had a good measurement for that. And the USGS had measurements for these other locations, particularly for Mount Hamilton. So that's why we do a comparison there between the 277 plus minus 3 milligal that we measured versus the 268 from USGS reports.
Yeah, it's really fantastic. I've never seen anything like this publicly. Well, I guess this is QED-C membership right now, but I haven't seen data like this before. Can you go back to, I want you to go back to your pin slide.
Okay.
Well, I already had a question prepared here, but John Kitching actually is asking one of my questions as well. He's saying spectacular results on pins. Brent, are those performance specs publicly documented? And you and I talked about this a bit, Brent, before. You have only been allowed as of 2021 that you have in your slide here, that we asked you to put there, because you have these results as of 2009, but because of various restrictions of US DoD, you were not allowed to release this data until now. Is that correct?
Yeah, that's right. This is the first time I was actually able to publicly present it in a non-restricted audience. So, but and to answer John's question, yes, there's a review article on quantum sensing that's out for publication. It's not been published yet. Once it is published, then I can provide a reference for it. AOSense is not one of the co-authors on it, but it included our results.
Yeah, that's fantastic. So is it safe to say that you have continued to work on your gyro and it's better than what you're showing here?
Yeah, if you search for kind of DARPA press releases, they'll talk a little bit about in this time frame after 2009 of various program managers will talk in trade journals about the types of things they were working on, which is basically trying to take performance that were demonstrated under static conditions and try to transition them to dynamic conditions. And so, AOSense is certainly engaged in various projects to advance the state of the art beyond what was achieved in 2009.
Great, great, wow. One other question. So what do you see now for AOSense and the market in general? Gyro, quantum gyros, research has been going on, really since about 2004 or 5, correct me if I'm wrong, where the funding really started to accelerate. Where do you think it goes from here now? Like in terms of, and what is the next, how it better said is, what is the next steps for AOSense in terms of, commercializing this technology? What are you focused on?
Well, we are interested in supplying sensors. So, and we're happy to either provide them as single axis, gyroscope accelerometers, or we're happy to integrate them together into an IMU, similar to previous speakers. And also, kind of have the similar vision to Paul and others, that you start kind of with some of the military applications that are most demanding and have the strongest need to operate in a GPS denied environment. But then over time, as we develop ASICs and integrated photonics for really reducing the swap of these devices as well as the cost, then we're also excited about meeting the needs of various commercial applications. Certainly there are those applications out there right now, commercial navigation that needs to be done underwater and they can't use GPS signals. So they're out there, but the thing is that they're more cost sensitive than certain DoD applications. So we need to really do some significant engineering to really bring down the cost. But the systems, once we really refine them and perfect them for the DoD applications, I really see no reason why we can't, if we find the right sources of funding for doing the development, see no reason why they can't really be benefiting commercial applications as well.